So today I want to talk about how to do problem solving for rotational kinematics and dynamics, and you'll see it's basically the same thing that we did in modules 2 through 4. So first of all, remember we change variables symbols for rotational motion. So instead of x, v, and a, we use theta, omega, and alpha, and the units for distance are going to be radians instead of meters. So you can see that the equations here, the format is exactly the same. The only thing that has changed is which alphabet we use for the symbols. And remember, we're going to use the sign to indicate direction. Positive is counterclockwise, negative is clockwise for the displacement, for the velocity, and for the acceleration. So let's start off with a simple problem. And again, we're going to use the same method that we used for module 2. So we're just going to use the goal method. As we read the problem, we're going to pull out anything that gives us a number, write it down, and then we'll figure out which equation we're going to use to solve what it's asking for. So a car accelerates from rest. So if it starts from rest, that means that the initial velocity, remember this time we use that omega, the curly W, initial velocity is 0, and the units for that are radians per second. With the tires undergoing a constant angular acceleration of 5.8 radians per second. So that tells us the angular acceleration, which is alpha, is 5.8 radians per second squared. The radius of each tire is 0.33 meters. So R is 0.33 meters. At t equals 10 seconds, what are the angular velocities? So for A, it wants us to find omega. For B, it wants us to find the linear velocity, which is v. For C, it wants us to find the angular displacement. Angular displacement is delta theta. Oops. Okay, let's try it again. The angular displacement, delta theta, and the distance traveled by the car, which is delta x. So those are the four things we're trying to find. All right, so what do we know? We know the initial velocity, we know the angular acceleration, we know the time, and we know the radius. So if I look at these equations, and I'll just put a check mark beside everything I know. Let's see, I know alpha, I know t, I know omega 0. Okay, so I can see that I can use the first equation to find omega. So for part A, all I'm going to do is just direct plug and chug. Omega equals omega 0 plus alpha t. The 0 plus alpha 5.8 times 10. So that's 58. And the units are radians per second. Okay, so that was pretty easy. Part B asks for what's the linear velocity. So we need to remember that the linear velocity and the angular velocity are just related by the radius. Right? So the radius is 0.33 meters. I know omega, so I'll just do 58 times 0.33, and I get 19.1 meters per second. So it's about 19 if I round it to two significant figures. So remember, A is the algebra, putting the number in, and L is looking at your final answer and making sure that it makes sense, it's not too big or too small, and that you have the right number of significant figures in the right units. All right, C, angular displacement. So that's delta theta. So I want to find delta theta. So that's either equation 2 or equation 3, because now I know omega. I could use equation 3, but for equation 3, I'm going to have to do algebra, and I'd rather just do straight plug and chug with things that I'm given in the problem. So let me just do equation 2. So delta theta, which is theta minus theta initial, is omega 0 t plus 1/2 alpha t squared, and just plug in my numbers. 0 times 10 plus 1/2. Alpha is 5.8 times 10 squared. And I get 290. And what's the units? Well, the units for distance is radians. Okay, so it's 290 radians that the car tire has rotated through. And then part D, what's the distance? Delta x is just, again, related by the radius, is delta theta times r. So it's 290 times 0.33, which is 95.7. And I need to round that to 2 sig figs, so it's 96. And the units for distance, linear distance, is meters. Okay, so that was pretty straightforward. That was mostly just sort of definitions and straight plug and chug. Let's do one where we have to actually do some algebra. All right, so I've got a dentist drill accelerates from 1.05 times 10 to the 4 radians per second to 3.14 radians per second. So units of radians per second tells us its angular velocity. The from means that's the initial, and the to means that it's the final. So omega 0 is 1.05 times 10 to the 4 radians per second. And omega final is 3.14 times 10 to the 4 radians per second. And the bit rotates through 1.88 times 10 to the 4 radians. So if it's got a unit of radians, that must be displacement. So delta theta is 1.88 times 10 to the 4. And these numbers are so big because the dentist drill, you know, it makes that real screeching sound. That's because it's going so fast. All right, so what I want to know in part A is what is alpha? The angular acceleration. So I want to find the angular acceleration. I know omega, and I know omega 0, and I know delta theta. All right, I don't know alpha, and I don't know t. So since I don't know t, I can't use either equation 1 or equation 2. So I need to use the third equation. So for part A, I'm going to use omega squared equals omega initial squared plus 2 alpha times delta theta. And I got to solve this for alpha. So we're going to solve it just the same way that we rearranged it in module 2. Delta theta is omega squared minus omega 0 squared. So subtract the omega 0 to the other side and divide by 2 times delta theta. And now just plug in my numbers. So I've got 3.14 times 10 to the 4 squared minus 1.05 times 10 to the 4 squared. Okay, so remember when you're doing things with exponents in it, if you have an exponent, EXP or EE button on your calculator, that's a good thing to use because it ties that times 10 to the 4 together with the number in front of it so you don't mess up. Otherwise, make sure you put a lot of brackets in. All right, so plug all that into my calculator carefully, and I get a big number, 23,290. Sorry, that's not delta theta I'm solving for, that's alpha I'm solving for. So it should have had alpha over on the left-hand side. And I noticed that because I was going back to look at my units, and then I realized that, no, hang on, I'm supposed to be solving for alpha. So units for alpha are radians per second squared. And let's see, how many significant figures do I need? So I got 3, 3, and 3. So I need to round it to 3 significant figures, 23,300 radians per second squared. All right, so for part B, now it says if it started from rest. So now we're changing our variable. So it's starting from rest, so omega 0 equals 0. How long would it take? So that means what's t? For the drill to accelerate to 7.85 times 10 to the 4 radians per second. So that's my omega final. All right, So omega final 7.85 times 10 to the 4 radians per second. All right, so now I want to find t, and let me erase what I had up here for what I know and what I don't know, because we've changed things. All right, so now I know omega, omega 0, and alpha, and I want t. So the first equation is the easiest one for me to use. So I'm going to use omega equals omega 0 plus alpha t. So t is equal to omega minus omega 0 over alpha. And so I've got 7.85 times 10 to the 4 minus 0. That's easy. Divided by alpha. And I'm going to use the unrounded number just to make sure I get the right number. 23,290. And I get 3.37 to 3 significant figures. And the unit is seconds. Okay, so it's pretty much just like doing the problems in Module 2. It's just that you have to use the different kind of alphabet. So that's kinematics. Let's move on to dynamics. So dynamics was when we introduced forces. And so remember, the rotational equivalent of force is torque. And torque is equal to R times F times sine theta, where F is how hard you push, R is how far you are from the pivot to where you apply the force, and theta is the angle between the force and that radius vector. And the units for torque are in Newton meters. So a torque, remember, that makes something rotate counterclockwise is positive. Torque which makes something rotate clockwise is negative. And you have to add if you've got more than one torque. So let's start off with a simple one. Let's just start off with a force of 55 newtons is exerted on the end of a door that's 74 centimeters wide. What's the torque if the force is exerted perpendicular to the door or at 45 degrees to the door? So our equation is tau equals RF sine theta. So we're just going to say, okay, I've got my F, I've got my R, and it gives me the angles and the things. So let me write down, so R is 74 centimeters. Remember, we've got to put that into meters, so divide by 100.74 meters. F is 55 newtons. All right, so what's the angle? So for part A, it says we're perpendicular to the door. So here's my door with a hinge. I'm applying my force perpendicular to the door. So the angle between R and F is 90 degrees. Okay, so that's going to be easy. So I'm just going to do torque is R. Let me write it out. RF sine theta. So that's going to be 0.74 times 55 times the sine of 90. And the sine of 90 is 1. So if I do that, I get 40.7 or 41. And the units are Newton meters. And again, I look back and I round off to the correct number of significant figures. And in this case, if I look at my numbers, I have 2 significant figures in 55 and 2 in 74. So I'm going to round off to 2 significant figures. All right, so what changes for the next one? Well, the only thing that changes for the next one is what the angle is. So if I draw my picture, now I'm applying the force at 45 degrees to the door. R and F are the same. So the only thing that's going to change is the sine theta. Go ahead, write down the same equation. So 0.74 for R, 55. And now it's the sine of 45. And remember, it's important, the angle that's important that you need to have is between R and F. Okay, so if I plug that into my calculator, I get 28.8, or about 29 Newton meters. So by not pushing perpendicular, I get a smaller torque. The maximum torque you get is when sine theta is its biggest value, and that's going to be when you're perpendicular. And you all know that if you're going to push on something to open a door, you push perpendicular to the door. Okay, so if I'm going to make something, put a force on it to make it accelerate, what's my equation equivalent to Newton's second law? So F equals ma is Newton's second law, and I know that A is just R times alpha. So if I put in for my torque equals Fr, and F equals m times A, which I'll put in R alpha, I get that torque is equal to mr squared times alpha. So the equivalent equation has an mr squared when I relate the force to the acceleration. And that mr squared we call the rotational inertia. So if you just have an object of mass m that's rotating in a circle, its moment of inertia is mr squared. And so then we say that torque is equal to I times alpha, where I is the moment of inertia. And the unit for that is going to be kilograms meters squared. What happens if I have something that has more than just a point mass? Well, then I have to do calculus. I have to integrate for all the objects' masses, how far away they are from the center. And so I have to add up, do a calculus integration. So I'm not going to expect you to be able to do that. If you need a moment of inertia, I'll give it to you. So the moment of inertia in general is usually just some fraction times the total mass of the object times its radius squared. And if you have a more complicated shape like a hollow object, then it gets a little bit more complicated. All right, so what else did we do? So we also talked about work in Module 6. Work in Module 6 was force times distance. Work for rotation will be the rotational equivalent of force, which is torque, times the rotational equivalent of distance, which is delta theta. So if you apply a force, it does a work, and that work changes the velocity. So we have sort of a work kinetic energy relationship as well. Okay, so let's do some questions with this. So I have a 20 kilogram child sits 1.5 meters to the left of the fulcrum of a massless seesaw. And we say no mass because then we don't have to worry about the moment of inertia of the seesaw. Then we put a 30 kilogram child 2 meters from the fulcrum on the other side of the seesaw. All right, so let's first of all, whenever we do problems like this, and in the next module where we do equilibrium problems, it's important to draw a picture. So I've got a 20 kilogram kid sitting 1.5 meters on the left, and a 30 kilogram kid, so let's draw a bigger kid, sitting 2.0 meters on the right. All right, so we want to know what's the net torque on the seesaw and which way will it spin. Okay, well, you sort of know from everyday life, if you've got the heavier kid sitting further from the center, it's going to go in the direction of the heavier kid. So we would expect that it's going to rotate around clockwise. But let's do a calculation and figure it out. So torque, there's going to be two torques on the seesaw, one from each kid. There's going to be a torque on the left and a torque on the right. So the torque on the left is going to be the force on the left times the distance on the left. Remember, torque is equal to R times F times the sine of the angle. And the torque on the right is going to be the force on the right times the distance on the right times the sine of the angle on the right. All right, so what's the force? Well, the force on the left, it's just gravity. The only force is weight. So it's going to be mg. So that's going to be 20 times 9.8. The torque on the right, so the force on the right is going to be mg again, so it's going to be 30 times 9.8. All right, so we're going to have 196 newtons and 294 newtons. All right, so let's put in those numbers now. So the force on the left is 196. The distance on the left is 1.5. And the angle, well, the angle is between R and F. And so if you look at the R is horizontal, the force is vertical, that angle is 90 degrees. So sine of 90. The torque on the right is going to be 294 for the force, 2 for the distance, and again sine of 90. And sine of 90 is 1. All right, so if I put that into my calculator, I get the torque on the left is 294 Newton meters. The torque on the right is 588 Newton meters. Okay, so I've got my units, I've got my numbers. Now I have to think about direction. So let's look at the torque on the left. So if I have a torque on the left, what I usually do is I'll take a pencil and I'll hold it at the fulcrum and I'll pull down or pull up on the side where the force is. So if I pull down on the left side of my pencil, that would make it rotate counterclockwise. So the left torque is going to be positive because it's counterclockwise. If I pull down on the right hand side where the heavier kit is, that's going to be rotating clockwise, so that's going to be negative. So if I'm going to get my net torque, I'm going to add up those two. If I add up those two guys, 294 minus 588 is going to be negative 294 Newton meters. And because it's negative, it's going to be clockwise, which is what we figured just from common sense. Okay, so it's clockwise because it's negative. And if you don't know from common sense, just do your math and you'll get a positive sign or a negative sign, and that'll tell you which direction it rotates. All right, what's the moment of inertia for the system? Well, the moment of inertia is going to be the moment of inertia for the kid on the left plus the moment of inertia for the kid on the right. Since they told us the seesaw had no mass, then we'll assume that the seesaw has no moment of inertia. So what's our equation? Well, I is just mr squared. So for the kid on the left, it's going to be 20 times 1.5 squared. For the kid on the right, it's going to be 30 times 2 squared. Right, so that's going to give me a moment of inertia of 165, and the units are kilogram meter squared. Now, I'm not rounding anything off at this point because I'm going to need to use these later. All right, last part. C, what's the magnitude and the direction of the angular acceleration? Well, the direction will be clockwise. It's going to go in the same direction as the net torque. And how am I going to solve for the angular acceleration? Well, the equation I'm going to use is tau equals I alpha. And I found my tau and I found my I. So I'm just going to use alpha is equal to tau over I. So it's going to be minus 294. And again, remember, the sign is important. We're going to put in the sign if we want to get what the direction is going to be. So I'm going to do 294 divided by the moment of inertia, which is 165. And I get 1.78. Sorry, negative 1.78. And the units for alpha are radians per second squared. Okay, so the negative sign again tells me that it's going to be clockwise. All right, then for my final number, I should go back and round everything to two significant figures, since it looks like that's what we're going to have in our thing. So I'm going to say minus 290 for my torque. For my moment of inertia, I'll say 160 kilogram meter squared. And for my alpha, I'm going to say minus 1.8. Okay, so again, remember when you're doing problems on the test, units and significant figures, I'll dock you half a point for when you miss them. Okay, so the problem that I want you to work on is a combination of rotational kinematics and rotational dynamics. So in this case, you have a meter stick, so it's sort of like the seesaw problem. You're pulling up on one end with 35 newtons, and you're pulling up on the other end with 12 newtons. Remember, the distances here are in centimeters, put them into meters. And I want you to do just basically what I did in the previous problem. So find out what's the net torque, what direction does the stick rotate. In part C, we tell you what I is, the moment of inertia, and I want you to find alpha. And then I want you to go back and do a kinematics, where if it starts at rest, what is its angular velocity 5 seconds after it starts?